Hello, it's Keith here, and this is lesson 3 of the Maxtile series of my Z80 assembly programming tutorials. What is Maxtile? Well, it's what you can see here. I did a previous example called MinTile, which was a simple multi-platform tile map. This allowed for XFlip, and it allowed for tiles basically, and simulated sprites using miniature tile maps. Maxtile is the successor. It also uses miniature tile maps for simulated sprites, but this time, as well as XFlip, it supports Y-Flip. It also supports fast fill, which is where the tiles are filled quickly with just a 2-color graphic. That's a fast fill example there. It also supports double height, which is using half of the source pattern data, so saving memory, and can be also used for a double height effect if you want to make things stretch out a bit. So it's designed as an enhanced successor to MinTile. It also supports a cached drawing mode, which uses a cache of the changes to draw to the screen so that we can save memory of not using a double buffer, but we can still get a reduced flicker effect by using that cache. So that's what we're going to be looking at today. We're going to be looking at the shared code today. We looked at the examples before, example 1 and example 2. That was example 2 you saw there. What we're going to look at today is the multi-platform code, which is common to all the systems, and this is the shared code that does some of the tile map drawing. So let's go over and let's take a peek. So the file we're looking at today is the Maxtile v1 file here. So as I say, the code here is shared and is common to all of the systems essentially. So at the start here we have some definitions for the sprite offsets. Now a lot of the Maxtile is designed to use a sprite object, which is a set of various values relating to a simulated sprite. So we've got definitions for a position of an X, Y, location in logical units, pairs of pixels, so I always use logical units, width and height in logical units, the memory address of the source tile map, because the sprites are drawn with a miniature tile map, it's all using the same code. That's intentional to save the amount of platform specific code. If we use the tile map code for the simulated sprite objects, that's less code to port, whereas if we were using the systems themselves, we'd have to have different sprite routines for each system, and some of them would be more and less efficient depending on different sizes of sprites. So it's very hard to make multi-platform sprite code effectively without a lot of work. So we're using the tile map. Now the patterns here is the address of this source pattern data. In MinTile only use 1 byte per tile. Maxtile uses 2 bytes, and so in most cases you'll be able to use the same pattern data for your sprites and your background, which wasn't really the case with MinTile because of that limitation of 1 byte per tile. We then have 2 caches for crops. Basically, we have a cropping routine which is very similar to the one I used in the simple series. This will calculate the, if a sprite is partially off the screen, it will calculate the area that needs to be drawn and the VRAM address of the drawing. Rather than calculate these if each time we need to draw the sprites, we calculate them only when the sprite moves and then use the cache data later on. Hopefully saves a little bit of time, and it could reduce some flicker if we're drawing directly to the screen and things. So we're caching that data, and we have one for the sprite and one for the background behind the sprite, because we all need to draw the sprite away and draw it in its new position. So that's why we've got those caches. We have some routines here for removing the sprite. We've got a routine here called get tilemap under sprite. And this will basically calculate the area of the tile map, the source tile map for the background, underneath the sprite. And this is so that we can flag the tile map to be redrawn if the sprite has moved. So that's what this is doing. The first thing we're doing here is we're getting the crop flag. If this is set, then the sprite is not on the screen, so we would just want to return in that case. Otherwise, we're getting the X and Y position, the width and the height, and then we're running this routine which will convert a logical unit coordinate into a tile coordinate, effectively dividing by 4. If the 0 flag is set by that, then the width and the height is resulting in 0, so we would return. Otherwise, we're shifting the background tile map address so that we've got the top left corner on the tile map of the sprite that we've got on the screen. Here we're then setting the carry and returning. Okay, so that's what that does. Do crop logical to tile, we just discussed that. Basically, we're taking the X and Y position, we're dividing them by 4, same with the width and the height. And then we're checking the width and the height to see if either is 0. And if they are, then we're returning with the 0 flag set. And that means there's nothing to draw, nothing logical to draw, because you don't want to try and do a loop of 0, because you're likely to end up repeating 255 times, just depending how your code works. But if the width is 0, there's nothing, or the height is 0, there's nothing to do. Here's our shift tile map code. Now this has actually been hard coded to either a 32 or 36 tile wide source tile map. The logic behind this is that the screen's 32 tiles wide, but you might want a small scrolling area, so we've allocated an extra 4 tiles for scrolling. Now rather than using any kind of multiplication routines that are more flexible, we've got this very crude hard coded one for those particular widths here. But basically what this routine does is it effectively takes the Y position and multiplies it by the number of bytes per line, and then adds that to the tile base, the base address of the source tile map, which is specified here. And we then take the X position and multiply it by 2, because there's 2 bytes per tile, and add that. So this is effectively calculating the memory address of the first tile based on an X and Y position in tiles here. So that's for, again, redrawing the tile map. And you can see it being used here. So here's the remove sprite routine. So what this will do is it removes the sprite by telling the tile map underneath the sprite that it needs to be redrawn. So we're using that get tile map under sprite routine there to calculate the tile map under the sprite. And then what we're going to do is we're going to flag it for redrawing. Now Maxtile, unlike MinTile, Maxtile, one of the bits of the tile number within the tile map is actually a flag for redraw. Bit 0 in each 16-bit value is the flag for redrawing. So all we need to do is set that to 1, and then when we redraw the tile map, those tiles will redraw, whereas the ones without that flag set will just simply do nothing because they've not changed. So what we're doing here is we're looping over the area defined by our sprite. The width is in D, the height is in E, and we're just setting all of the bits to 1 here, which will flag them for redraw in the background. So that's what we're doing there. This is for doing the background tile map. There's another routine for flagging a sprite. Now this is slightly different here. We're basically checking the sprite and seeing if the bytes are set to transparent. The value for a transparent tile is FFF2. That is the completely transparent tile, not partially transparent. That means a tile that does absolutely nothing. So we've got to check all of the tiles before we flag them. Here's the routine that's flagging the tiles for redrawing within the sprite tile map. But we're checking that value here, and we're ignoring the bottom bit of the first byte because that is the flag for redrawing, and so we don't want to consider we don't want to worry about if a transparent tile is set to be redrawn or not, because redrawing it does nothing. We could actually just try and redraw them. It's just that would cause an extra execution to the draw tile routine for no reason, because the tiles are blank. The routine will actually just skip if it's asked to draw a transparent tile, so it's just a time saving there. But before we run that routine, basically what we're doing here is we're getting the height and width of the draw area, converting those to tiles. We are calculating the count of tiles with a crude multiplication here. We are loading the address of the source tile map for the sprite here into HL, and we've got our tile count here in BC at this point, and our source tile map in HL. So that's what all this is doing, and as I say, just flagging those tiles. Now that's being used for flagging a sprite tile map. This is being used to flag an area under a sprite in the background tile map, but there was a couple of other routines for the background tile map. There's a very crude one called reset to tile map, and this just flags an entire range of tiles, not checking for transparency because there shouldn't be any blank tiles in a background tile map. You could layer them if you had a lot of processing power to do a parallax effect, but not really viable on Z80 systems. But anyway, so we're just flagging all the tiles in the tile map here, all BC of them, a BC count. Now you can use this for flagging the entire tile map if you need to redraw everything. If you've scrolled down or up, you might want to flag the bottom or top of the screen just to redraw those. You could use it for that as well, but it's not going to work for the left and the right because we'd need to actually skip over some tiles before doing our flagging. So that's not applicable for that. But we have reset tile map part where we can specify a top left corner, a width and a height, and an area of the background tile map will be flagged. So that's what this is doing here. So that's for basically when the screen's scrolling left and right, redrawing the left-hand side or the right-hand side accordingly, flagging them for redrawing there. So that's what that's doing. Now, we do have another kind of flagging routine, and this is a little bit more complicated. Now, let's suppose we have two sprites on our screen. Now, for this example, this sprite will never move, but this sprite is going to move. And every time it moves, we need to remove the background and draw the sprite in the new position. But there's one problem. What happens when this sprite overlaps this one and then moves away? Now, this sprite will, of course, be redrawn. And when it moves away, the background here would be redrawn because it knows that the sprite is left. But that would mean this sprite had been taken away. So this sprite needs to be redrawn again. But we don't want to redraw this sprite every frame because in most cases it doesn't need redrawing. But what we want to do is detect when this sprite needs to be redrawn because of something that has happened to it because of another sprite. Now I refer to this as being a dirty sprite and it needs to be redrawn and cleaned up. So what we're going to do is we're going to check the tile map behind the sprite and see if any of those tiles have been flagged for redraw. Because if the sprite has been overlapped and moved away, those tiles behind it would have been flagged for redrawing, because the sprite always marks the tiles behind it for redrawing, and so that means that this sprite must need redrawing as well, because it's now been dirtied by that sprite moving in front of it. So what this routine here does is it basically checks all the tiles behind the sprite, sees if any have changed, and then flags those tile sprites for redrawing. But unfortunately it's a little bit more tricky than that. We're having to expand the area a little bit, and we're also, when a tile behind the sprite is being flagged, we're actually flagging 4 tiles in the sprite for redrawing, and the reason for that is that our foreground sprite might not be aligned exactly to one tile boundary. It might be halfway across a tile, or halfway down, or even a quarter of the way across. We allow our sprites on some systems to move in pairs of pixels if it's possible on that system. So we do, when one tile in the background has changed, we actually change the neighbouring 4 tiles in the sprite, because, as I say, it might not line up exactly. It might be offset by an amount. So what we're doing here is we're getting the X and Y position and the width and the height. We're increasing the X and Y position if our scrolling position is set here. We're then basically going to just calculate our source tilemap address here, and what we're going to do is we're going to test the tile in our background here, and if the tile in the background has been flagged for update, we're going to set the 4 tiles that could relate to in our sprite, and we're going to flag those all for redrawing here, and that's what that's doing here. This is going to repeat through the entire sprite for each frame, if we are worried about our sprite getting overwritten. In the example, I'm only doing this for the player sprite. All the other sprites are moving anyway, so they're always going to need redrawing every frame, but the player sprite might not, and so that is allowing for the sprite to not be deleted away by a sprite coming across in front of it. So that's what that does. Now, zero sprite in cache, this is something that existed in Mintile as well. As our sprite is moving around the screen, we're going to need to remove the background behind it, but if our sprite only moves a little bit, some of that background that we might want to redraw will actually be covered up by the sprite itself in the next frame, and so it's a waste of time drawing that background again when it's just going to be overwritten with a sprite again. And so what we're doing here is we're checking to see if that's the case, and we're zeroing the update flag, clearing that flag if the sprite is about to be redrawn in that position again anyway. Now again, unfortunately, because we're allowing for half tile shifts and things, it is a little bit tricky here, and so what we're doing here is we're effectively just increasing the X and Y position here by 1/2 tile here, and we're decreasing the width and the height by 1/2 tile here, and this is basically shrinking the area that we are considering for clearing, because a half shifted sprite with partial transparency would otherwise have glitches around it. That was a problem with the Mintile version, so that's why we're doing that. It's to basically accept that the outer area of the sprite is going to need redrawing no matter what because of that. And then what we're doing here is we're going to basically look at each tile within our sprite, and we're going to basically check if any of them are partially transparent. Now, partially transparent tiles, even if they're in the middle of the sprite, pixels that are in those tiles should show the background through, and so in those cases, even if it's right in the middle of the sprite, it still needs to draw the background behind it every frame anyway, and so in those cases we are going to skip over that sprite even if we thought we might need to do it, and we're going to not change that tile. Now if we get down to here, then it's been decided that there's no reason to actually update this tile in the background tile map. The sprite is going to overlap it and we won't be able to tell the difference. So here we're just clearing the update flag of the background tile map, and then we're just repeating until we've done the entire sprite here. We're using various data. We're using the width of the tile map here for the sprite. We're loading that in and adding that to move down in the sprite tile map, and we're of course updating. We're using the background tile map as well, which we're adding here. So that's it. You don't need to do that. You could disable that routine, but it would mean you were drawing things for no reason. And on these 8-bit systems with bitmap screens, drawing tiles, even 8x8 pixel tiles, takes an unfortunate amount of time. So anything we can avoid drawing to the screen reduces flicker and that kind of thing. So that's why we're doing that. Now, cache tilemap CLS, this is the clear screen routine, which effectively instigates a redraw of the background tilemap. So what we're doing here is we're basically loading in the parameters of the background tilemap. The screen base is the VRAM destination. The width of the tile map in bytes here we're calculating, and we're calculating the width and height of the screen in tiles. That should always be 32 by 24 on most of these systems, so that's what we're doing there. And then what we've got here is various shifting commands for half and quarter tile shifts of the background tile map on systems where that is possible. So we're tweaking the VRAM destination. Now, for convenience, because this is multi-platform code, all of the code can only draw in full tiles. So if we're half a tile shifted, we're actually going to end up with a dirty area around the screen of half a tile on both sides. Now, my plan for this is simply to draw a border around the screen to cover that potentially dirty area. That's the simplest solution. The only other alternative would be to have tile drawing routines that could draw half a tile. That would add a lot of extra code. I simply don't think it's worth it for 8-bit systems. It's too much work. So to say, I'm intending this to either move in full tile, to scroll in full tile jumps, so 8-pixel jumps, or if you're using half tile jumps, then you would want to draw a 4-pixel border around the sides of the screen. If you're using quarter tile jumps, you wouldn't need to draw a 6-pixel border around both sides of the screen to cover up any potential dirty areas. As I say, if you look at the example I ran earlier, you will see, if on this example here, as it scrolls, there is a sort of a glitchy area of 1/2 tile around the screen, and that's because of that effect. And so really this should have a 4-pixel border drawn on it. I just haven't put it in this example. It's a minimal example, so I didn't put that code in. But that's why there's that glitching. It's because of that half tile scroll, and the code can't do that. So that's calculating those memory offsets there, and then we're running draw tile map to actually draw the tile map to the screen. Now, there's another drawing routine for actually drawing the sprite. So we would pass the IX pointer to point to the sprite object here, and what this is doing is it's loading in the previously calculated information about the drawing area from the crop cache, and then it's going to draw the tile map to the screen just using the same draw tile map routine for regular software bitmap tile maps, or if we're using hardware sprites on a few systems, we would run the alternate version for those hardware sprites. But that's all that's doing. It's the same draw tile map routine. We're just loading in the parameters from the crop cache here. Now, we're actually coming onto the crop cache right now. So how does the crop cache work? Well, we've got a version of doCrop, which is basically the same version with a few tweaks and corrections that was shown in the simple series before. So this, in the past, it just calculated all its values and stored them in the registers. This version, we're now transferring them and storing them in a cache for later. And the intention of this originally was to reduce flicker, because we could calculate the crop early on and then do all of our drawing later. But also with the cache, that's not so much of a problem. But by caching it, if the sprite's not moved, when we need to redraw it again and redraw the background, we can use the previously calculated information to do that. So it does save us some time there as well. So all this is doing is running the doCrop routine here, and then it's storing the various results in the crop cache offset of this sprite object. The flag is set to 0 if the sprite is entirely on screen. If it's off screen, it's set to 1. So that used to be in the carry, but we are storing it in a register here. And here is the doCrop routine. So this is almost the same as before. It's just had a few tweaks. So what we're doing here is we are loading in the values for the height of the screen. And so this is the minimum Y position, the top of our screen, and also the height of the screen for when we're doing the crop, because we actually have to change these a few times. We change them when we are calculating the background, and when we're calculating the drawing of the sprite, they're slightly different. And the intention was that maybe you're working with multiple screen areas if you've got a split screen effect or something going on. So these are actually configurable now and stored in various values in memory here. So what we're doing here is we are taking the X position of our sprite. So here's our sprite, and we're subtracting the top of the screen, effectively nudging up here like that. And so this will basically, if the carry is set, then the sprite is partially off the top of the screen. Otherwise, we're just skipping over. Now, if it's partially off the top of the screen, we need to do two things. We need to calculate the amount of the sprite that is actually on the screen. We're first checking if any of it's on the screen. If it's entirely off the screen, we're going to skip. We're rounding to tiles here. so that we're making sure we're working in tiles, because we remember the minimum drawing unit is 1 full tile. Now, if the sprite is partially off the screen, we can't draw half a tile or a quarter of a tile, as I said before. So what we're going to do is we're going to skip 1 full tile, and we're going to shift the draw position of the remaining part so that it's equivalent, so that the sprite moves smoothly off the screen, even though the drawing might miss parts of that sprite. And so what we're doing here is we're effectively calculating the correct offset for the part that we're going to draw based on the fact that part of a tile is not going to be drawn. We're then storing the new Y position here in C. What we're then going to do is we're then going to calculate the new height. So we're adding the height here. We're then subtracting the logical height of the screen, converting to tiles. And we're storing the amount to crop from the bottom in D here. So we've calculated the new height here. And what we're going to do here is we're going to see if we need to remove anything from the source tilemap, because if the sprite object is off the top of the screen, we need to remove some of the source drawing data. The source drawing data is in IY, and so what we're doing here is working out the number of bytes for each line of our sprite object here, and then we're just effectively skipping that number of lines from our IY pair here. So we've cropped the height of the sprite, the top and the bottom of the sprite as required for if it's off the top or the bottom of the screen. We're now going to do the same for the left and the right. So we're getting the far left position and the width of the screen here into IX, and we're then going to take the X position, subtract the left hand side position, so calculating for cropping on this side of the screen there. And again, see if we need to do any cropping. If we do, we're calculating the number of tiles to crop here, seeing if that's the entire sprite, if the sprite's entirely off the screen. Otherwise, we're calculating the shift offset for the drawing position, saving the new drawing position. And then we're calculating for the crop on the right hand side. So we're adding the width of the sprite, subtracting the width of the screen, and seeing if there's anything to crop. And if there is, we're converting it to a number of tiles here. We're then updating and calculating the new width here. And then finally, what we're doing here is we're updating IY, skipping any number of tiles from our object, considering that it might be off the left-hand side like that. Now, once we've done that, we've calculated all of our cropping. If we've got to this point, we're clearing the carry because we're notifying the calling routine that the sprite is indeed drawable. If at any point, though, the sprite has been found to be completely off the screen, what we're doing is we're actually going to return here, and so we're running this all off-screen routine. Now, there was actually a glitch in the original version of this routine. This routine was in my simple series. The version there had a limitation where if the cropping object was actually bigger than the screen in any of the drawing area, I should say, in either axis, it wouldn't work. Now, that generally wouldn't be a problem for most cases, but I wanted this routine to be sufficiently flexible that you could draw the screen in multiple windows, either because of convenience of reducing the draw time to reduce flicker, or if you wanted to have a split screen effect or a super huge sprite that was being drawn to the screen. So that has actually been fixed here. I had to make a few tweaks to the position that I was doing the calculations. The height calculations had to be moved here because originally I was doing them up here, but it was causing problems later on. So I've changed this very slightly, and this is a slightly better version of the code. Anyway, we're going to continue with Maxtile. Next time we're going to look at the drawing routines that actually pass control from the tilemap drawing. The draw tilemap routine we saw today that passes the control over to the platform specific code. You can download all of the source code for today's example if you want, and you're welcome to use any part of it in your own program projects, even if they're commercial. As I've said before, Maxtile is very complicated. It's unfortunately is the case that when for the things I want to do later on with my multi-platform games, I needed something this advanced, but it becomes quite hard to work with. If you want something simpler, see Mintile or Grime. Grime had a simple tilemap routine. And also, if you look at the platform-specific modules of Maxtile, each one just draws a single tile to the screen. So you're welcome to take that code, take parts of it, and use that in your own examples if that helps you out. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.